overhead for exchanging these large size tokens that are way larger than 127 by 10K. The next thing is that how the token is validated. So there are several approaches. In the existing approach, one is the token validation approach is implemented in a cloud. It could be in the edge or in the traditional cloud as well. When a device receives it communicates to the cloud for the token validation. In the semi-distributed approach, the gateway intercepts it redirects the request to the cloud or the external entity for authorization. And in the distributed approach, the access control logic is implemented in the device as well. When you get the request, it validates the token and then it starts the request. But there are a few problems here. The first thing is that there is a round-trip delay to communicate to the cloud. So devices that need to serve a request real-time, like medical IP devices, that are constantly sending their updates, or even the physician are constantly monitoring their physical health condition. In the smart healthcare scenario, cannot be applicable. And there is also a token delivery time in the centralized and distributed approach. You see, this is the constraint network. This is the lossy network. So if this large size token delivered over there, there is a huge communication and fragmentation overhead. And also there is a computation overhead to validate the token in the distributed approach. The device itself, they have very few megahertz processor, and they try to validate it, also it makes them slow. So what is our approach? We're saying, don't need to implement this access control logic to the cloud, or even in the edge. So implement in the gateway. So by delegating the task to the gateway, we have some advantages. The first is that the gateway performs faster than the constrained IP devices. It is closer to the device than the clouds. And the third thing is that these gateways are not battery powered. So this is from this perspective we propose this solution. And we implemented a prototype using quantum devices running a remote quantum operating system, and the devices we use are remote. And here is the experimental network. So these devices are communicating in IPv6 and they are in the IPv4. So here, if you take a look here, we are able to reduce the service delivery time significantly, because the token do not need to deliver to the resource constant network. So the gateway takes care of everything. For the same reason, the gateway validates the token. So that here actually we are able to reduce the energy consumption as well for receiving the token and verifying the token. So we eliminate those overhead from this device. Now come the device to device. Okay, because the client is operating, the user is operating an IPv4 network. But when two clients device want to communicate to each other, both of them are in the IPv6 network and in the resource constant device. Now how actually we can take care of this? There are kind of two scenarios. Either we have to follow the star topology so that all the packet route through the gateway, because we are delegating the task to the gateway. Or even in the 6-loop network, it could be a diode graph. So here the scenario will be like this. Say for example, 1 want to send the request to 2. So it has to route through the gateway. Because still, although the shortest part is 152. So here, then how can we reduce the token delivery communication latency? So we propose, okay, compress the token before sending it over the lossy networks. Let's see how we gain the advantage. So here you see we're able to reduce the number of fragments significantly. So that's why we're able to reduce the token delivery delay. And the same thing, we're able to reduce the energy consumption from the sender side and the receiver side. From the sender side, it has to fragment the token and send it. For sending each token fragment, there's a energy consumption by the radio transceiver. And also, so we are able to reduce it. And also for the receiver side, there is two energy consumption. One is by the CPU to reassemble the fragments, and one is by the radio transceiver to receive the fragments. So we are able to minimize those energy consumption. So based on this, we are able to publish one journal to conference paper, and also we also publish a patent. So now, okay, devices are operating perfectly. They join the network, they can talk to each other, they send a request, the service device authorize and serve the request. Now, here comes the network attacks. Okay, wireless attacks. We didn't talk about the wireless attack. Devices are working perfectly fine, but the adversary can be malicious, that is co-located close to the same radio range with the devices, and they can try to disrupt the communication. So here we address the fragmentation, network attacks. So the 6LoWPAN is a protocol that is used that enables UDP packet to get fragmented in the 6LoWPAN network. So here the thing is that it enables UDP packet fragmentation in lossy and lossy IP networks. Usually UDP packet doesn't, we know UDP packet has to be sent in a single fragment, but this additional layer allows to send the UDP packets over lossy links. But the problem with the 6LoWPAN fragmentation mechanism is that it doesn't have the support for payload or fragmenting payload integrity verification. That's why a receiver cannot identify if a fragment has been modified when actually it was routing through an intermediate node. And it doesn't have fragment authentication mechanism. As a result, it doesn't detect IP address spoofing attack. In addition to that, there is no way a receiver can identify if a fragment has been replayed. And the poor buffers management scheme in 6LoWPAN make the devices vulnerable to buffer reservation, reassembly buffer reservation attacks. So what is our proposal here? So in the fragmentation header, we propose nonce field and cryptographic datagram tag field that enables the receiver to identify replayed fragments. We propose a MAC, message authentication fields, that enable devices to verify the integrity of the fragment. That's how they can detect any altered or modified fragments. We completely introduce a new fragments, we call it retransmission fragments, that enables a receiver to identify which fragment has been modified, and it sends the sender, okay, only this fragment has been modified, just send that fragment. Right now in the current implementation, interestingly, it doesn't have this functionality. Therefore, it first gets all the fragment, reassemble it, and then actually identifies, okay, there is some problem. Some fragment is modified, but it doesn't know which fragment is modified. So the sender has to set all the packet fragments, even a single fragment is missing or modified. So for introducing this, only it can send the missing fragments. And we also propose adopts cryptographic IPv6 address to prevent IP address spoofing. We propose a reputation-based buffer management scheme to prevent reassembly buffer flow. So we implement a prototype using remote devices running config operating system. The way it works, there's 3 devices, one is Bob, one is Alice, one is Mallory. So we configured Mallory, so devices are routed from Bob to Alice, and this Alice is configured such that it modifies the fragments or alters the fragments or duplicate the fragments after 500 milliseconds or 1000 milliseconds or 1500 milliseconds. So to simulate the fragmentation attack. So here you can see in the alteration of fragmentation attack, for our case, because we proposed these additional fields, so we are able to increase the effective number of packets compared to the quantity when 6LoWPAN is under alteration attacks. And even for buffer reservation attack, the packet delivery ratio for our scheme is way better than the contemporary, the base quantity buffer management scheme. Based on this work, we published a paper in Code-Aspire. Okay. Now the next thing is that devices are operating very good, and we can defend the network attacks. Now it is possible that adversary can use IoT devices as tools to commit crimes. How it works? Let's consider some hypothetical scenarios. For example, medical IoT devices like a IP-enabled pacemaker that is implanted to a patient body, it can be hacked into that will be life-saving for a patient. And even in the connected car scenario, like vehicular ad hoc network, providing false information to another device could be life-threatening for the other cars. So that is also could be devastating. And even it is possible, we need to resolve some dispute. For example, in the smart transportation, to resolve the dispute for traffic ticketing or violation of traffic rules, this dispute can also be resolved. So here, actually, our goal is to provide a trustworthy forensic investigation framework. So the question is that how actually we can collect the evidence and store the evidence securely. That's the main challenge. So what we did, we considered the interaction and communication that take place between device to device, device to cloud, and device to user as evidence. We collect this evidence, and then we store this evidence in a distributed, decentralized public ledger similar to the one we are using to find, something like this. So here we collect the interaction and preserve it in a decentralized, distributed public ledger. So how it works? So we collect the interaction. Using the interaction, we make a transaction. And then this transaction is pushed to the public blockchain. So why actually we choose this model? So there are a few things. The first thing is that we eliminate a single entity's control over the evidence storage media. So why we need that? Because during investigation, the stakeholder of an IDOB system can collude to each other to tamper with the evidence, to manipulate the outcome of an investigation. So there is no way they can do it here. And also, by doing this, we have non-functional requirement. We achieved some non-functional requirement. We are able to avoid the single point of failure and also ensure high availability of the evidence during the investigation. And finally, the interesting thing is that this is a public blockchain, right? Public ledger. So the evidence, the sensitive information will be there. So we provide a mechanism that ensures the anonymity and privacy of this evidence as well, that the public can have. So we implement a prototype using Ethereum blockchain platform. So here actually we wanted to observe, because of this forensic load, how the performance varies. So here we see that, yeah, there is a little bit slight increase in the end-to-end delay because of the additional overhead for the forensic payload that is added to the normal request. And also there is a little bit energy consumption on the IoT device side that is a little bit increased because they have to perform some hash and signature operation to create this transaction. So, but this is a trade-off, so we're giving a new facility, we're enabling forensic investigation, so there's a little bit energy consumption there. But yeah, for better good, yeah, I think we can use it. So yeah, we published 2 conference papers. One is under review and another, one conference paper and one post-study info. Now, the last thing, okay, these are the modules of the of our proposed framework. Now, how actually we can integrate our proposed framework IoT Curator with a mobile and distributed IoT-based system. So we have to show that it works, the whole system can provide a secure ecosystem in our IoT network. So we first propose, this is a newer computing model. So IoT devices are smart enough, they are using for various purposes. So we think from different perspectives. What if we can use, so here actually we propose a framework that actually enables to create ad hoc or proximal cloud using IoT devices. So, and the goal was that the computation then running on a smartphone, the data parallel computation that follows the MapReduce model. So if you can create an ad hoc cloud, proximal cloud, not the edge cloud, not the traditional cloud, even closer. So here actually our goal was there. So we know IoT devices are resource constrained, but here our goal was that that when there are a large number of devices, so can we think from a different perspective? When the device, our goal was to harness the CPU cycle of the devices that are idle. So we have to create a large number of devices. That's why we use a simulation environment. We call it COSA. Actually, we are able to create a large number of virtual devices, IoT devices. And we consider a word count problem that follows the MapReduce model, and we outsource this in the Aura Cloud, and we are able to see, if there is sufficient number of IoT devices there, we are able to outperform the computation that is running on mobile devices. But if you take a look here, the Aura is mobile, the devices that smartphones and also the devices that perpetuate in Aura, they are mobile and they join the network and leave the network anytime. For example, in a building, a car, a smart car, it can participate in the Aura Cloud for an hour, and after 1 hour it might leave. Even the mobile devices that are roaming from one building to another. So here you see the HSC IoT and boot IoT proposed that provides a secure network admission. The PHIP, during device-to-device communication, it provides the security. For authorization, we have the delegated based access control scheme. To mitigate the network attack, we have the SecuPAN. And to ensure the privacy of these mobile devices, we have HSC IoT, boot IoT, and PHIP. And to resolve any dispute and auditing because of the task offloading, task outsourcing, yeah, we can use it PHIP for that. So we publish a journal and conference based on this work. So this is the summary of contribution. We start with analyzing the vulnerability of these IoT devices, IoT-based system, we identify threats, and then we ensure the security, we provide secure network admission scheme, privacy and authentication scheme, resource efficiency scheme, and also we mitigate network attacks. We enable forensic investigation in IoT environment, and we showed that our proposed scheme, proposed framework is compatible, can be deployed to IoT-based system. And here are the security modules, and these are the research question that we did, and these are the contributions. Based on our contribution, now we can say, yeah, we ensure security, privacy, and trustworthiness of computation and communication that take place in resource-constrained IoT devices and low-power and lossy networks, based on analytical evaluation of threat models and adoption of lightweight cryptographic schemes. This is the publication that are included in this dissertation. And I have also worked on cloud, some contribution on cloud when actually I was going through this journey. One of our paper got best paper award from IEEE. And Bain Technology, they conducted a survey on 533 users. They asked the user to select top 3 barriers for IoT solution. And 45% of them said security. So we believe that our proposed IoT curator will encourage more people to embrace, to adopt IoT-based solution. And also it will open the opportunity for newer computing models using IoT-based system, the one we showed all, something like this. And some research, future research work. So also I found that there is some problem with their current secure service registration scheme. They are vulnerable to service impersonation. We can propose some scheme there. And also you see that we can use energy efficient software distribution approach scheme in lossy network, and the autonomous forensic investigation. Sometimes when actually I was doing research on this IoT forensic framework, then I see the typical case that the literature when I reviewed, they identify a threat, identify incident, they investigate assign. But this is a real-time system. Sometimes it might be too late, and the device are mobile. They might commit a crime and leave the network. So the incident identification, we can make it autonomous, smart, using machine learning techniques or and even some part of the investigation it is also possible to make autonomous. So also the challenge is that beyond of large number of data there. So which data will be the important piece of information is also a challenge to find that. So actually some of the project we are working on, Sani and Jayan we are working on, so we have some plan to submit a couple of papers on that in the end of April. So I would like to thank Dr. Hasan for guiding me and giving me direction. I would like to thank to my wife and my family members, and also all the friends at UAB, the colleagues, and also all the faculty members and staff of UA's CS department. So that's all about my presentation. So you can have questions, comments, and concerns. I'll try my best to give the answers. Thank you.
Thanks, Mahmoud, for the presentation. Now we have time for question and answer, and question and answer will have 2 parts. The first part is the public session, where anyone is welcome to ask questions, and after that we'll ask the public to leave because the committee members would like to ask some questions in private. So if you have any questions, now is the time to ask.
Okay. Can you please go to the page 34? I guess it was 34. You were talking about addition and saying that you found that it makes the token secure enough.
34, right?
Yes. 33 and 34. Yeah, you were talking about addition, that you use addition and this addition makes the system secure enough. I just want to see, have you done any tests, any kind of evaluation, and this addition is secure against what sort of attacks?
Oh, this is a part of the ECQ cryptography well established. So here, so I have a backup slide for that. This is what I'm saying. So that's why actually, because of the time constraint, I could not explain all of those. Just give me a moment. So this is the traditional ECQV approach. Okay. So it's smaller to there. So here, what they do, they provide the ID and a random variable, and the certificate author issue a certificate that contains the credential, and they use this certificate credential like this, and then compute the, here you see this DU and QU, okay, and also it computes the and the certificate have the PU, device ID, and some additional information. So during the authentication phase, so it gives the key, it extracts the PU, the certificate value, the Ragib value is encoded here. So it creates the hash, and it does the multiplication, and it computes the temporary key, and then this is also kind of combined public key cryptography. You understand? So the combined public key cryptography is secure. This, for the same reason, this is secure. So the way we propose is that you see they encode this identity and all of this stuff in the certificate. So that means every time you want to change your identity, you have to go and contact to the certificate authority. We eliminate that part. Okay, we don't need that. What we did, okay, from this storage secure channel, so there is no issue with that because this is a combined public key cryptography. So 2 points, they add it, there's a new point. So we cannot do the reverse from there. And here, what we did, the modification, in our proposal scheme, we say, okay, the certificate authority, you don't need to take care of all this stuff. Whatever the credential you use to compute those identity, send it to the device. The device will take care of everything. So what the device do? The device use those and create these things. And then actually, this verified proof that they trust the certificate authority. Okay. So then when it's received this, it only add and verifies it. This is also a combined public key cryptography. Got what I'm saying?
Yeah, but still, I'm not sure how if you get the wrong value, so you're getting the wrong value.
Okay, so say for example, for the identity impersonation, so I am saying, okay, I have things like how the certificate works. The certificate works is that we are communicating to a server. The server sends a certificate. So what is written in the certificate? Their IP address, their public keys that are signed by, right? So the same thing here they are doing. So that means they're saying the public key I'm going to use is not spoofed because I have the proof of the certificate. So we're saying eliminate the certificate. We don't need the certificate. If two parties trust a certificate authority, we don't need the certificate because it stores the credentials and use the credential from session to session to create new keys. And they trust the certificate authority and just add the certificate authority keys and to validate it. So if you want to go into detail how it works, this is how it works. So this is the proof of correctness of this algorithm. So we have the P and QA. We add it and we generate this one. Okay. So how it works? So RP and del. So what is this del? The del is K into G. This is a random variable generated from one device to another device. So then actually, if you follow this equation, so it adds those two and it's S. How the S generated? The S is generated by the certificate authority. It sends securely, and you see this S, when it compute the S, it has the private key of the certificate with it, of the certificate authority UT. So S is like the signature of the certificate. But it's not a long certificate, it's a key of 256 bits, something like this. So this is the correctness of this algorithm. So that means the correctness works like that. The QP should correspond to this according to the elliptic cryptography. So here, if you add those two things, follow this step, you see that yes, we can come to that conclusion. Did I answer your question properly? No convenience here?
In the scheme, for a lot of the steps, you have kind of dependence on a central identity provider and a kind of assumption of the always-on internet, and then the network that you're connecting to and coming from in your IoT space is the unreliable component. What impacts does, for example, say your Internet of Things network becomes detached from the production network, so to speak, the global network. What happens inside of that network? Like how does it fail? Let's put it that way. Like, does it fail terribly, or does it fail like gracefully?
That's a very good question. So you see there is two phases here. The first phase is the authentication phase, network admission phase. For the network admission phase, the global entity has to be online always. When it comes to the network admission phase, so here they trust the certificate authority. Only if it stores the CSQCA, that's fine. They don't need to contract going to do this. But for the network admission, even in USB secure, when we were joining, we use EAP TLS or UAP password-based TLS, the one I showed a comparison with our one. So it has to be online for the network admission. For peer-to-peer communication, no need.
Okay, so basically, once you get on the network and you've got your state set up efficiently,
Exactly.
you can move around the network whether a particular gateway is online or not. With the
It's fine.
network.
Because for peer, that's how actually we detach the contact of system.
I mean, I guess I'm just kind of curious. I mean, I think that's solid. I guess I'm just kind of curious. What situations, like, does a car not start when I can't connect to the global internet, or like what happens? Like,
Then actually one thing is that so we just trade off with the performance. We have to fall back to the traditional system. We use the certificate and those system, but those are memory overhead, but it's okay for disaster.
Okay.
We can fall back to the.
Okay, so you just go back to
it is the implementation perspective, because we cannot address all of those things in a single paper.
Totally understand. I was just kind of curious.
But it's a valid concern.
Yeah.
So I have a couple of points. So just to go on that. So it's like, if you have a switch button started, if the switch is broken, then you go back to the key and
Okay. Yeah.
plug the key to start, right? Do the old way. So, so now related to that. So I look at the design space, having the network which is not ultra reliable, and then the devices which are not, powerful or doesn't have long battery. So now let's assume that I have a reliable network. Okay, so the networking issue is not there. So how does your design space change?
Yeah, that's why actually we compare it with the existing scheme. So that's why, I mean, whatever we do it in the existing scheme. So, give you
So where you have your 7 bullets, you can kind of look at those 7 bullets.
So here, if you take a look here, so we compare with the EAP TLS and EAP PSK, pre-shared key and good. These are the IETF standard, and the RFCs are available. So even if the EAP PSK and the EAP model MD5, they don't recommend right now. So the TLS is commonly used. We use for authenticated to our shiplet server when you join UABCQ. So even if we can use this model, we can use this. I mean, although in the research, when actually I was starting concern the resource consent device, but I also feel the same way. Yeah, we are comparing with the scheme that are currently standardized. So even, yeah, we have a plan to disclose some IPs based on this our innovation. So we're on the process on that actually.
So then, I would say, okay, so I would do it kind of, step by step, right? So I would say, okay, my network is fine, I have no unreliability in the network, or I have the bandwidth available in the network. Let's say, 5G becomes common. Then I would say, all right, so, does anything change, in all these 7 bullets, am I going to see anything that's going to be different? Then I would say, all right, so let's take care of the networking problem. Now let's assume that my device has enough battery capability and enough compute. So maybe add 1 at a time. So let's start with battery capability. So energy I can sustain. Okay, that's not an issue. Now what changes?
Okay, let me summarize your question. So let's take off the IoT from here. So we want to use it for the regular system. Yeah, we can. That's the thing I keep saying.